This call is now being recorded.
Okay, so in the last lecture we have started the numericals or the problems based on the calculation of the bending stresses, and in the last lecture we have solved a total 3 problems. The first 2 problems we have solved based on the rectangular section where the cantilever beam is subjected to the point load and another cantilever beam is subjected to the UDL. So in that, how to use that particular bending moment formula for the M calculation, that we have discussed about the problem number 1 and the problem number 2. Then what is the third problem we have solved? It is related to the unsymmetrical I section. So the unsymmetrical I section is given, but in that particular statement, the type of beam and the type of load, it is not mentioned. Only one cast iron bracket is there, and that shape of that particular cast iron bracket is in the form of unsymmetrical I section. And for that particular, we have to calculate the maximum bending stress. So what we have done, as the I section is the unsymmetrical, so we have to calculate the Y bar first. Then we have to calculate the moment of inertia. So as the section is unsymmetrical, so that big formula we have used by using the Y1, Y2 and Y3 calculations. Then Y bar we have calculated, and whatever the Y bar we have calculated, that represents the position of neutral axis from the bottom side, because Y1, Y2, Y3, that distances we have taken from the bottom side. That is one reference line we have considered. Therefore, whatever the Y bar you will get from that Y bar formula, that Y bar also we have represented from the bottom side, means we have represented the position of neutral axis. And then from the total depth of that particular I section, we have subtracted that Y bar, and remaining Y bar above the neutral axis, that also we have represented on the figure. And then we have calculated Ixx1, Ixx2, Ixx3. At the end, we have made the addition, and Ixx means your total moment of inertia. And then by using the first Y bar and by using the second Y bar, we have calculated the 2 bending stresses, and out of that we have decided that which is the maximum. Okay, so that problem we have solved for the unsymmetrical I section. Now today we will solve one more problem based on the bending stress calculation. So here the problem number 4 is there. So what that particular statement, just read. T section. So what if the section is given? That is T section with flange. T section with flange 200 by 50 mm, that is B into D. The dimensions of the top flange, because the T section, it is having only upper flange, it is not having the bottom flange. If the inverted T is given, then that flange will be comes to the bottom side. But if the simple T section is there at the top side, the flange is there, its dimensions are given, that is the flange of 200 mm by 50 mm and wave 50 mm by 125 mm. The wave dimensions are also given. Its horizontal distance is 50 mm and vertical distance is given as a 125. Wait. Yes, vertical dimension is 125 mm and is used as a cantilever beam. Here the type of beam is also mentioned, that is the T section is having the flange dimension 200 by 50, wave dimensions 50 by 125, and it is used as a cantilever beam of span 2.5 meter. The type of beam is given cantilever beam, its total length is 2.5 meter, subjected to UDL of 20 kilonewton per meter over full length. So whatever the cantilever beam is there, that beam is subjected to the UDL on entire span. Full stop. Determine maximum stress in the beam. Determine maximum stress in the beam. Full stop. What is the nature of maximum bending stress? So whatever the bending stresses we are calculating, after that we have to calculate the maximum. For example, one stress you will get the 20 Newton per mm square, and another stress you will get the 30 Newton per mm square. After the comparison, what I can say that 30 Newton per mm square, this is the maximum bending stress. But that 30 Newton per mm square, this is the tensile stress or compressive stress. That means in this particular numerical, first of all, we have to calculate the 2 bending stresses. Out of that, we have to select maximum stress and their nature. Whatever the maximum stress we are deciding, nature of that particular maximum bending stress is tensile or compressive, that we have to decide. Also, we have to draw the stress distribution diagram. That means bending stress also we have to calculate. Then we have to calculate the maximum bending stress, and out of that we have to decide that whether it is under tension or the compression. And also we have to draw the stress distribution diagram. So here from this particular statement we can clearly say that the T section is given. So here I will write the given parameters. So what are the given parameters are there? That is, as per the flange dimensions are given. Flange 200 mm by 50 mm. Okay. Then wave dimensions are also given. How much? That is 50 mm into 125 mm. Okay. Then W, UDL magnitude is given 20 kilonewton per meter. So I have to convert in Newton per mm. So 20 into 10 raised to 3 kilonewton is converted. Then meter is converted into mm. 10 raised to 3, 10 raised to 3, it will get cancelled. So you will get 20 Newton per mm. So this is the W value we have calculated. Then length of the beam is given 2.5 meter is equal to 2000 mm. And here I will draw the figure also as a cantilever beam is given. So cantilever beam subjected to the UDL on entire span, its magnitude is 20 kilonewton per meter. This is point A, this is point B, and distance between point A and B is given as a 2.5 meter. And we have to calculate the bending stresses. Now here the type of beam is mentioned. Cantilever means here we can easily say that whatever the stresses you will get, the two stresses above the neutral axis, the cantilever beam is subjected to the tension, and below the neutral axis, the cantilever beam is subjected to compression. That means we can easily say that which will be the tensile stress and which will be the compressive stress. Both tensile stress and compressive stress are the bending stresses. Please keep in mind. Both tensile and compressive are the bending stresses. Sorry, 2.5 means 2500 mm. Okay, so this is the statement. Now by using the flange and the wave dimensions, here I will draw the T section. So try to draw this particular figure in your notebook also. The T section is given. Okay, so this is the T section. So flange dimensions are 200 mm by 50 mm. Okay, so this is the flange dimensions. This is the center line of that particular flange, and this is the wave. This is flange. This is called as a wave, and its dimensions are also given. Its horizontal dimension is 50 mm, and vertical dimension of the wave is also given as a 125 mm. Okay, and this is the center line of this particular wave, and this is bottom. This is called as a reference line, because from this particular only we have to take the y1 and y2 distances. So the vertical rectangle will be considered as a section number 1, and this flange, it will be considered as a section number 2. So these are the projections which are required to draw the stress distribution diagram. Okay, so this is the T section. The flange is given, wave dimensions are given. Now this T section is not symmetrical about the x-axis. This T section is not symmetrical about the x-axis, because if you think about the center of this particular T section, above neutral axis their section will be different, below neutral axis the section will be different. Therefore we can easily say that the unsymmetrical I section and the T sections are comes under the category of unsymmetrical section. Therefore here it is not possible to use the direct formula y bar is equal to capital D divided by 2. So for that purpose we have to use the big formula. So first of all, in order to use that particular formula, which one? Y bar is equal to A1 Y1 plus A2 Y2, because only two sections are there, divided by A1 plus A2. Okay, so these are the formula. Now first of all calculate the A1. So A1 is equal to 125 into 50 is equal to, and A2 is equal to 200 into 50. So what is the area A1? Please do the calculation. 125 50. Calculate the area. Yes, A1 is equal to 6250 mm square and here it is 10,000. Okay, A1 we have calculated, A2 we have calculated. Now similarly find out the Y1. Now Y1 is the distance of section 1 or the CG distance of section number 1. It is exactly at the center. So here I will represent. This is the your Y1, and from bottom reference to the CG of the section number 2, this is Y2 distance. Please tell me Y1 is equal to 125. Y1 is equal to 125 divided by 2 is equal to 62.5 mm, and Y2 is equal to this 125. I have to take as it is plus 125 plus, yes, 125 plus
25.
125 plus 20 divided by 2 or directly 25. So Y2 is equal to 150 mm. So Y1 we have calculated. Y1 means the CG distance of section number 1 from the bottom line, and Y2 means the CG distance of section number 2 from the bottom line. So this 125 we have to take as it is, and the CG distance of the section number 2 is equal to 125 plus 50 divided by 2. While taking the Y1, Y2, Y3 of that particular section, the remaining distances below that particular all the sections it will be considered. Therefore here I have considered 125. So now Y1 is calculated, Y2 is calculated. Now go for the Y bar calculation. Y bar is equal to A1 Y1 plus A2 Y2 divided by A1 plus A2. So A1 6250 into 62.5 plus A2 10,000 into Y2 150 divided by 6250 plus 10,000. So what is the Y bar? Do the calculations properly and tell me the Y bar. Yes, 116.34 mm. So this is the Y bar. So if I will represent this particular Y bar means I have to draw the neutral axis. From the bottom side we have calculated the Y bar means we have to represent the neutral axis on this particular figure. So here I will draw one center line. So this center line, it represents the neutral axis, position of neutral axis from the bottom side. So from the bottom side, how much amount of distance is there? That is Y bar is equal to 116.34 mm. And then remaining distance, Y bar is equal to, what is the total height of this particular beam? What is the total height of this particular T section? 125 plus 50.
175.
175 minus 116.34. Then what is the remaining Y bar? Yes, 58.65 mm. Okay, I have to represent on the figure also. That is Y bar is equal to 58.65 mm. Okay, so this is the two Y bars we have calculated. Now, but here we can easily say that the type of beam is mentioned. Type of beam is already mentioned, that is cantilever beam. Now, above the neutral axis, cantilever beam is subjected to the tension or compression. Above the neutral axis,
Tension.
tension. Above neutral axis, it is tension, and below neutral axis, it is compression. Therefore, whatever the Y bar is represented below the neutral axis, that is Y bar is equal to 116.34 116.34. This y bar is also called as a yt, or it is also called as a y bar t. Okay, because it represents the tension, and above the neutral, sorry, yc, below the neutral axis it is yc, and above the neutral axis, if your section is subjected to tension, what is the y bar we have calculated? 58.65, and it is under tension. Therefore, this y bar is called as a y bar t. But in the whatever the last problem we have solved, in the last problem, the type of beam is not mentioned. Therefore, we cannot say that the above neutral axis y bar is subjected to the tension or compression, or below neutral axis y bar is subjected to the tension or compression. But here the type of beam is mentioned. Therefore, whatever the two y bars we have calculated, that is first y bar is equal to 116.34, which is also called as a y bar c, and the second whatever we have calculated, this is called as a y bar t, or we can call it as a yc, or it is called as a yt. So y bar is equal to y. We can use any sign conventions. Now here two y bars we have defined, but again the section is unsymmetrical. Therefore, we have to calculate the ixx1 and ixx2. Then we are having the formula capital I is equal to ixx is equal to ixx1 plus ixx2. Now first, ixx1 is equal to BD cube by 12 of section 1 plus A1 in
Sir.
bracket y bar minus y1 bracket square. So what is the B for the section number 1?
Yes. हॅलो सर.
Yes.
सर ती 116.34 आपण 175 मधनं का मायनस केलं सर?
Please check. What is the total length of this particular T section? 125 plus 50 from top portion to the bottom portion. What is the total height of the T section? 125 plus 50. This is 175. Okay. From this 175, if I will subtract 116.34, I will get another y bar which is present above the neutral axis. हा 116.34 हा जो y bar आपल्याला मिळालाय तो कुठून मिळालाय? खालच्या बॉटम रेफरन्स लाईन पासून त्याच्या न्यूट्रल ऍक्सिस पर्यंत. पण वरच्या पोझिशन पासून न्यूट्रल ऍक्सिस पर्यंतचा वाय बार किती आहे तर तो आपल्याला माहित नाहीये. त्यामुळे आपण काय केलं, टोटल हाईट मधून न्यूट्रल ऍक्सिसचा खालचा पोर्शन जर सबस्ट्रॅक्ट केला तर न्यूट्रल ऍक्सिसचा वरचा पोर्शन आपल्याला काय मिळतोय, फाइंड आउट होते. देअरफॉर आय हॅव सबस्ट्रॅक्टेड दिस 116.34 फ्रॉम दिस टोटल हाईट 175. समजलं? म्हणजे न्यूट्रल ऍक्सिसचा खालचा पण वायबर आपल्याला काढायचा आहे आणि न्यूट्रल ऍक्सिसचा वरचा पण वायबर आपल्याला फाइंड आउट करायचा. गेटिंग?
Yes sir.
Okay, now we have to calculate the Ixx1. What is the value of B? What is the value of B for the section number 1?
50 mm.
50 mm. And what is the value of D for the section number 1?
120 mm. 125 mm.
5. So here 50 into 125 cube divided by 12 plus A1 we have calculated 6250. Now here which y bar I have to take? Y bar minus y1. Which y bar I have to take here? 116.34 because y1 distance we have taken from the bottom side. त्यामुळे बॉटम साइड पासून न्यूट्रल ऍक्सिस पर्यंत जो y bar आहे तोच y bar आपल्याला Ixx1 आणि Ixx2 कॅल्क्युलेशन करताना कन्सिडर करायचं. सो 116.34 minus y1 distance is equal to 62.5 bracket square. Therefore Ixx1 is equal to, what is the value of Ixx1? Do the calculations properly and tell me the value of Ixx1. Yes, what is the value of Ixx1? 26.25. Please check. 26.25 into 10 raised to 6 or 4?
6.
10 raised to 6 mm raised to 4. Do the calculations properly. BD cube by 12 plus A1 in bracket y bar minus y1 bracket square, and you will get the value of Ixx1 26.25 into 10 raised to 6 mm raised to 4. Please check, others, please check your answers. Ixx1 is equal to 26.25 into 10 raised to 6 mm raised to 4. 10 raised to 4 or 10 raised to 6? Make the square of the bracket y bar minus y1 bracket square.
6 sir. 6
Many
बरोबर.
times you are not making the square, therefore you will get the answer wrong. Therefore, please make the square. Y bar minus y1 bracket square is there in the formula. Yes, 26.25 10 raised to into 10 raised to 6. Ixx1 is calculated. Similarly, calculate Ixx2 is equal to BD cube by 12 plus A2 in bracket y bar minus y2 bracket square. So value of B means horizontal distance of the section number 2, 200 into vertical distance 50 cube divided by 12 plus area E2 10,000 in bracket y bar once again 116.34 minus y2 distance 150 bracket square. Therefore, Ixx2 is equal to, find the value of Ixx2. Y bar minus y2 bracket square is there. So make the square. Yes, what is the Ixx2? Yes, 13.41 into 10 raised to 6. 13.41 into 10 raised to 6 mm raised to 4. Please check your answers. 13.41 into 10 raised to 6. This is the Ixx2. Okay, and then we have to calculate total I. Capital I is equal to Ixx is equal to Ixx1 plus Ixx2. Make the addition 26.25 into 10 raised to 6 plus 13.41 into 10 raised to 6. So you will get total
39.66 into 10 raised to 6. 66 into 10 raised to 6.
into 10 raised to 6 mm raised to 4. So this is the total I, that is moment of inertia. Only we have to make the addition of Ixx1 and Ixx2. So 39.66 into 10 raised to 6. This is the total moment of inertia about the neutral axis. Ixx1 represents moment of inertia for section number 1. Ixx2 represents the moment of inertia of section number 2. But total I, capital I, it represents the total moment of inertia about the neutral axis. So now I is calculated, y bar is calculated. Now we have to calculate the bending stresses. Now, next, we have to calculate one parameter once again. Whether bending moment is given in the statement, it is not given, but the type of beam is mentioned. So let us see. As per condition of cantilever beam, we have to calculate the capital M. So cantilever beam subjected to UDL on entire span. What is the M formula?
WL square by 2.
WL square divided by
2.
2. WL square divided by 2. This formula is applicable for the cantilever beam subjected to UDL. So W already we have converted in Newton per mm. So 20, length 2500 square divided by 2. So what is the M value? Bending moment, capital M. M value is equal to
62.5 into 10 raised to 6.
62.6 Newton mm. Here also length square is there. Sometimes many of students are not taking the square of length. 20 into 2500 divided by 2. You will get the wrong answer. Therefore, please check that particular formula whether only L is there or L square is there. So 62.5 into 10 raised to 6. This is the moment. Now we have to calculate the bending stresses. So bending stress. First, stress due to y bar is equal to y is equal to yt. So what is the yt? What is the value of yt above the neutral axis? 58.65. So 58.65 mm. Therefore, we are having the formula m upon I is equal to sigma upon y. So here I can write capital Y bar is equal to y is equal to y bar t or only yt. So m 62.5 into 10 raised to 6 divided by moment of inertia 39.66 into 10 raised to 6. Sigma we have to calculate y or yt 58.65. Therefore, sigma is equal to, what is the value of sigma? Or we can call it as a sigma t. Sigma is equal to sigma t. Sigma is equal to sigma t. So what is the answer? 92.42. Correct. 92.42 Newton per mm square. Why we get the sigma t? Because whatever the y we have considered, it is considered above the neutral axis. आणि न्यूट्रल ऍक्सिसच्या वरचा y बार हा आपण काय कन्सिडर केलाय तर yt. Why? तर कॅन्टिलिव्हर बीम मध्ये न्यूट्रल ऍक्सिसच्या वरचा पोर्शन काय असतो? टेन्शन असतो. देन सेकंड, stress due to, again, y bar is equal to capital Y is equal to yc is equal to 116.34 mm. So this 116.34 it is present below the neutral axis, and below the neutral axis of portion आपण काय consider केलाय तर compression. Therefore we have taken yc. So once again m upon I is equal to sigma upon y. So here capital Y is equal to y bar is equal to yc. Therefore once again m 62.5 into 10 raised to 6 divided by 39.66 into 10 raised to 6. Sigma is equal to y bar 116.34. Therefore you will get sigma is equal to sigma c. What is the value of sigma c then? Sigma c is equal to, why sigma c? Because yc we have taken below the neutral axis was 183.33. 183.33 Newton per mm square. Newton per mm square. So these are the two stresses. Both stresses are compressive. Sorry, both stresses are bending stresses. We have taken yt, that is 58.65. You will get the answer 92.42. We have taken y bar as a yc 116.34. You will get the bending stress as a 183.33. That means you are having the two bending stresses. Out of that, one is tensile and one is compressive. Both sigma t and sigma c are called as a bending stresses because they are developed when the bending of the beam is taking place. But what is our requirement? We have to calculate the maximum bending stress. Now, if I will compare both the stresses with each other, means if I will compare the sigma t and sigma c to each other, which is the maximum bending stress? Whether sigma c is maximum or sigma t is maximum?
Sigma c.
Sigma c is maximum. Therefore, final answer I can write, that is maximum bending stress is equal to 183.33 Newton per mm square. Why? Because sigma c is greater than sigma t. And what is the nature of that particular maximum bending stress? Please tell me what is the nature, whether it is tension or compression.
Compression.
Compression. Therefore, once again, the nature of maximum bending stress is compression. The nature of maximum bending stress is compression. So like that, we have to write down the answer at the end. They have asked the bending stress calculation also. They have asked the maximum bending stress also. But if I have to calculate the maximum bending stress, what is my requirement? I have to calculate the two stress values. If I will calculate the two stress values, then and then only I can go for the comparison. Kutla maximum and kutla minimum. Therefore, here I have calculated the two bending stresses in the form of sigma t and sigma c. I have compared both, and after the comparison, it has been observed that the maximum bending stress is the sigma c. Maximum bending stress is the sigma c, which is equal to 183.33 Newton per mm square. Maximum bending stress value पण मिळाली. But what is the nature of that particular maximum bending stress? That is C as a compression. Therefore, we have considered sigma C as the maximum bending stress. मग त्याचं nature काय असणार आहे? Compression. So like that, we have to write down this particular two sentences at the end in the form of maximum bending stress and their nature. So this is about the bending stress calculation for the T section. This is about the bending stress calculation for the T section. So whatever the last problem we have solved in the last lecture, similar procedure is there, but last problem we have solved for the unsymmetrical I section, which consists of a total three sections: bottom flange, wave, and the top flange. But in case of a T section, it consists of only two sections, that is top flange and the wave. Okay, so we have drawn the figure as per the statement given. We have calculated the y bar, we have calculated I, and then by using the yt and yc, we have calculated the bending stresses. Now here we have to draw the stress distribution diagram. Let us see. This is the vertical line. Okay, this is the vertical line, and already I have told the tensile stress is always represented at the right side, even it is minimum or even it is maximum. Tensile stress हा कॉम्प्रेसिव्ह पेक्षा जरी मिनिमम असला किंवा जरी कमी असला तरी पण तो वर्टिकल लाईनच्या राईट साइडलाच आपल्याला काय करायचं आहे, रिप्रेझेंट करायचं. सो सिग्मा टी इज प्रेझेंट अबव द न्यूट्रल ऍक्सिस, देअरफॉर ऍट द टॉप रिजन दिस इज sigma t is equal to 92.42 Newton per mm square, and at the bottom side below neutral axis it is subjected to compression. Therefore, sigma c is equal to 183.33 Newton per mm square. And if I will join this particular 2 points, so here at the center point, the bending stress is equal to 0, and it is maximum at the top side of the beam and the bottom side of the beam. This is called as a stress distribution diagram. So like that, we have to draw the stress distribution diagram in front of the T section, where the tensile stress is always represented at the right side of the vertical line, even it is minimum, even it is maximum. And the compressive stress we have to represent at the left side of that particular vertical line, even it is maximum or even it is minimum. So there is a separate 1 or 2 marks are there for this particular stress distribution diagram. Therefore, after the calculation of both the stresses, maybe bending, that is in the form of tensile and compressive, you have to draw the stress distribution diagram. So simply we have to draw the sigma t at the top side if it is under tension, sigma c at the bottom side for this particular T section, because below the neutral axis it is subjected to compression, and like that you have to represent the diagram. So this is about the T section, in which we have calculated the bending stresses in the form of tension and in the form of compression. So this is the problem. Now, the next problem, again based on the T section. The next problem based on the T section, again we have to calculate the same parameter, but one extra parameter they have asked at the end of the statement. So just read the statement carefully first, the problem number 5. Let us see the two rectangular sections. Sometimes the figure of the I section, T section, it is not mentioned or it is not given in the problem. Their statement is given, tangent dimensions are given, wave dimensions are given, and by using that particular statement, you have to draw the figure. Okay, so here the two rectangular sections of 50 mm by 150 mm are joined together. The two rectangular sections, both the rectangular sections are having same dimensions, that is 50 mm by 150 mm are joined together to form T section shown in the figure. The T section is once again T section is given if the sagging bending moment is 4 kilonewton meter. Sagging bending moment means value of the bending moment is given as a 4 kilonewton meter is applied to this particular beam, full stop. Find stresses at extreme fiber. Stresses at extreme fiber means we have to calculate the bending stress at the top of the beam and bending stress at the bottom of the beam. Therefore, the statement is given like that. Find the stresses at extreme fiber. Extreme fiber means top portion of the beam and the bottom portion of the beam, because at the center point, at the neutral axis, the bending stress is totally equal to 0. And total force due to tensile bending stress. We have to calculate the total force. We have to calculate total force due to tensile bending stress. Tensile bending stress means we have to calculate the tensile force which is produced or which is to be obtained from the tensile bending stress. The tensile bending stress जर आपल्याला माहित असेल आणि त्या बेंडिंगचा क्रॉस सेक्शनल एरिया जर आपल्याला माहित असेल, जर स्ट्रेस आणि एरिया माहित असेल तर आपण त्याच्यावरचा फोर्स आपण काढू शकतो. कारण आपल्याला माहित आहे सिग्मा इज इक्वल टू फोर्स अपॉन एरिया. जर फोर्स काढायचा असेल तर सिग्मा इंटू एरिया. मग स्ट्रेस जर तुम्हाला दिलेला असेल, बेंडिंग स्ट्रेस दिलेला असेल, त्या बेंडिंगचा जर क्रॉस सेक्शनल एरिया तुम्हाला दिला असेल तर वी कॅन कॅल्क्युलेट द फोर्स विच इज कॉल्ड एज ए टेन्साइल फोर्स. कारण हा फोर्स काढताना आपण कुठला स्ट्रेस कन्सिडर केलाय? टेन्साइल. तर तो आलेला फोर्स पण कुठला येणार? टेन्साइल फोर्स. जर हा स्ट्रेस काढताना जर तुम्ही हा स्ट्रेस सिग्मा जर कॉम्प्रेसिव्ह कन्सिडर केला तर आलेला फोर्स पण तुम्हाला कुठला येणार आहे? कॉम्प्रेसिव्ह येणार आहे. Therefore, here in this particular statement, we have to calculate the bending stresses also, and we have to calculate the total force due to tensile bending stress. बेंडिंग स्ट्रेस मुळे आलेला जो काय टेन्साइल फोर्स आहे, that force we have to calculate. Okay, so this is the statement in front of you. So whatever the previous problem we have solved, based on this only we have to calculate the bending stresses. Now here just write down all the given parameters and try to solve this particular problem in your notebook and tell me the answers of the y bar and the moment of inertia. Same problem like previous problem. So the given parameters, the dimensions are given 150 mm is D, 50 mm is B, capital M is given 4 kilonewton meter is equal to 4 into 10 raised to 6 Newton mm. But here one important word is mentioned, that is sagging bending moment. Sagging bending moment. So sagging bending moment is applicable for the simply supported beam. Please keep in mind, this is very important. Sometimes the type of beam, type of load is not mentioned in the statement, but we have to calculate the tensile and compressive. But in that particular statement, either word sagging, let us see here, sagging, or another word is hogging bending moment. So sagging bending moment is applicable for the simply supported beam. Please keep in mind, write down these particular words in your notebook. Sagging means type of beam is the simply supported, and hogging means type of beam is cantilever beam. And from this particular sagging, I have identified the type of beam is the simply supported beams, and from that I can see that above neutral axis, in case of a simply supported beam, above neutral axis, the portion is under tension or compression. Please tell me. For the simply supported beam,
Compression.
compression. For the simply supported beam above neutral axis, the portion is subjected to the compression, and below neutral axis, the portion is subjected to tension.
Tension.
To the cantilever beam. Therefore, here the sagging word is mentioned, means we have to take the type of beam as a simply supported beam, and hogging, if it is mentioned in any statement, the type of beam is considered as a cantilever beam. If the type of beam and type of load is not mentioned in the statement. Now in this particular statement, type of beam we can identify by using the sagging, but the type of load is not mentioned. But here it is not required because directly 4 kilonewton meter direct bending moment value is given. But the sagging word is mentioned in order to identify the type of beam, whether it is simply supported or whether it is cantilever. Therefore, take this particular two important words in your notebook. Sagging means simply supported beam and hogging means cantilever beam. Okay. So M we have converted. That is 4 into 10 raised to 6 Newton mm. Now, if I have to draw the T section, so once again I will draw the T section. Let us see here. The two rectangular sections are joined together. So this is one rectangular section. Its dimension is 150 mm by 50 mm. This is the one section. And if I will join another vertical rectangle to this section, I will get the T section. So the dimension of this vertical section is once again 50 mm, and their vertical dimension is also 150 mm. So this is the section number 1. This is section number 2. This is the bottom reference line from which we have to calculate the y1, y2 distances. Okay. So this is the figure. So here, this is the y1 distance, and this is y2 distance. Okay, now please tell me immediately what is the y bar value. Before that, let us see. A1 we have to calculate, A2 we have to calculate, then y1 we have to calculate, y2 we have to calculate. Please tell me one by one. Area A1 and A2. Let us see. For both the rectangles, the dimensions are same. That is 150 into 50. So you will get the cross-sectional area 7,500 mm square. Similarly, A2 also 50 into 150, 7,500 mm square. From the figure, yes, y1 is equal to 150 divided by 2, means center position of section number 1 from the bottom side. So 150 divided by 2 means 75 mm. Y2 means the center position of section number 2. 150 I have to take distance as it is. त्याचा सेंटर पोर्शन कुठे आहे बरोबर 50 च्या सेंटरला. सो 50 डिवाइडेड बाय 2 इज इक्वल टू 175 mm. Okay, so this is the 175 mm. Now please tell me y bar. Simple formula a1 y1 plus a2 y2 divided by a1 plus a2. Tell me the y bar. This y bar we have to locate on the figure as a position of neutral axis. So I will draw the neutral axis. So this is called as a neutral axis. And then tell me the value of y bar from the bottom side. So this is the, yes, what is the y bar from the bottom side? 125 mm. Please check 125 mm. Y bar is equal to 125 mm. So here I will write y bar is equal to 125 mm. Okay. Now please tell me the type of beam is the simply supported beam. So below neutral axis, what is the 125 we have considered, whether it is YT or YC?
YT.
YT, because in case of a simply supported beam from the sagging, we have identified that the type of beam is the simply supported beam. And in case of a simply supported beam, below neutral axis, your portion is under tension, and above neutral axis, your portion is under compression. Okay, so whatever the Y bar we have calculated as a 125 mm, that Y bar will be considered as a YT. Because below the neutral axis, the section is tension. So this is YT. And then what is the remaining Y bar? Total height is 200. Another Y bar is equal to 200 minus 125. So Y bar is equal to 75 mm. So this is 75 mm. And this Y bar is equal to YC 75 mm. Okay, so below the neutral axis, Y bar is 125 mm as a tension, because below neutral axis it is subject to tension. Therefore, 125 I have considered as a YT. Then what about remaining above the neutral axis? This 75 will be considered as a compression. Therefore, it will be considered as a YC. Okay, have you understood this particular part? How the YT and YC should be mentioned according to the type of beam. Below neutral axis under tension, आणि न्यूट्रल ऍक्सिसच्या खालच्या बाजूला जो काय वायबार आपल्याला मिळाला 125, त्याच वायबारला आपण काय म्हणतो, तर YT म्हणतोय, कारण न्यूट्रल ऍक्सिसच्या खालचा पोर्शन हा टेन्शन मध्ये आहे. आणि वरच्या बाजूला जो काय आपल्याला वायबार मिळाला तो किती मिळालाय, 75 mm. आणि न्यूट्रल ऍक्सिसच्या वरचा पोर्शन सिम्पली सपोर्टेड बीम साठी काय असतो, कॉम्प्रेशन असतो. त्यामुळे तोच वायबार आपण ऍज काय कन्सिडर केला, YC कन्सिडर केला. सो नाउ यू गॉट YT YC. नाउ कॅल्क्युलेट द Ixx is equal to Ixx1 plus Ixx2. Now please tell me the value of Ixx1 directly. BD cube by 12 plus A1 in bracket Y bar minus Y1 bracket square, and another Ixx2 BD cube by 12 plus A2 in bracket Y bar minus Y2 bracket square. Now here in Ixx1 and Ixx2, which Y bar we are taking for the calculation? Yes?
125.
Yes, which Y bar we have to take for the calculation, 125 or 75? 125.
YT.
First Y bar. Yes, first Y bar, whatever we have calculated. And in addition to that, here in the formula, Y1 is present and Y2 is present. Y1, Y2 distances we have taken from the bottom side. त्यामुळे बॉटम साइड पासून न्यूट्रल ऍक्सिस पर्यंतचा जो वाय बार आहे तोच वाय बार आपल्याला इथं काय करायचा आहे, पुट करायचा आहे. सो प्लीज टेक दिस पर्टिक्युलर इम्पॉर्टंट नोट. नाउ प्लीज टेल मी द व्हॅल्यू ऑफ Ixx1 and Ixx2. Do the calculations properly. Value of B, value of D is given in the figure. A1, A2 is given. Both Y bars are given. Out of that, we have to calculate, consider the bottom Y bar. Y1, Y2 distances are given. Tell me the value of Ixx1 and Ixx2.
Sir, Ixx1 20.31 into 10 raised to 6.
Ixx1 is equal to 20.31
into 10 raised to 6.
2131 into 10 raised to 6 mm raised to 4. This is Ixx1. Please check others. Please check your answer. Yes, 20.31 into 10 raised to 6 mm raised to 4. Others, please check your answers. 20.31 into 10 raised to 6 mm raised to 4 Ixx1. If you have calculated Ixx1, then calculate Ixx2. Ixx2, value of Ixx2 for the section number 2. Find the Ixx2. Y bar minus Y2 bracket square is there. Therefore, don't forget to take the square of that particular bracket.
89.06 into 10 raised to 6.
How much?
89.06 into 10 raised to 6. Ixx2.
89.
Yes, sir.
Yes, what about others, please?
32.81 into
Yes,
10 raised to 6.
32.81. Omkar, please check your calculation part. 32.81 into 10 raised to 6 mm raised to 4. Yes, 32.81. Others, please check your answer. 32.81. BD cube by 12. Take the value of B properly. Take the value of D properly. Area A2 is same. Yes, 32.81 into 10 raised to 6. Then make the addition. Capital I is equal to Ixx is equal to 20.31 into 10 raised to 6 plus 32.81 into 10 raised to 6. Then total moment of inertia.
53.12 into 10 raised to 6.
How much?
53.12.
53.12. Yes, correct. 53.12 into 10 raised to 6 mm raised to 4. Okay, so this is 53.12 into 10 raised to 6. This is the total moment of inertia about the neutral axis. Now, I we have calculated, y bar values we have calculated in the form of yt and yc. Now, calculate stress. Stress due to first y bar. Stress due to first y bar is equal to yt. What is the value of yt? What is the value of yt we have calculated? 125.
125.
Yes, 125 mm. So use the formula m upon I is equal to sigma upon y. So m 4 into 10 raised to 6. I we have calculated 53.12 into 10 raised to 6 sigma divided by. So here I can write y is equal to y bar is equal to yt. So here 125. Therefore, sigma is equal to. Then second, stress due to y bar is equal to yc is equal to 75 mm. So m upon I is equal to sigma upon y. In front of that, y is equal to y bar is equal to yc. So m 4 into 10 raised to 6. Once again, m is equal to 4 into 10 raised to 6 divided by I. 53.12 into 10 raised to 6 is equal to sigma is equal to y 75. Therefore, here sigma is equal to sigma t. Here sigma is equal to sigma c. Tell me the value of sigma t first. Yes, sigma t value 9.41. Correct. 9.41 Newton per mm square. 9.41 Newton per mm square. This is a tensile stress because here we have taken yt distance for the further calculation and yc sigma c 5.64 Newton per mm square. .64 Newton per mm square. This is the compressive bending stress because here during that calculation we have taken yc as a y bar distance. So sigma t and sigma c we have calculated. Sigma t and sigma c we have calculated. And if I will compare both the stresses, which is the maximum stress? Sigma t is the maximum stress. Therefore, I can easily say that the maximum bending stress is equal to sigma t is equal to 9.41. So here I will write maximum bending stress is equal to sigma T is equal to sigma is equal to 9.41 Newton per mm square. Maximum bending stress. This is the maximum bending stress. Now, next parameter we have to calculate. They have asked in the statement, that is force due to tensile stress. Force due to tensile stress. Now, please tell me, from this particular figure, the tensile stress is induced below the neutral axis or above the neutral axis? From the figure,
below.
बिलो द न्यूट्रल ऍक्सिस. म्हणजे टेन्साइल स्ट्रेस जर न्यूट्रल ऍक्सिसच्या खालच्या बाजूला येत असेल तर टेन्साइल फोर्स पण त्या न्यूट्रल ऍक्सिसच्या कुठे येत असणार आहे? खालच्या बाजूला असणार. म्हणजे बघा, हिअर आय विल मेक द हॅचिंग लाईन्स. न्यूट्रल ऍक्सिसचा खालचा पोर्शन मी काय केलाय? हॅचिंग लाईन इंडिकेट केलाय आणि तोच पोर्शन ही विल आय विल ड्रॉ सेपरेटली. सो दिस इज द न्यूट्रल ऍक्सिस. लेट अस सी. दिस इज कॉल्ड एज ए न्यूट्रल ऍक्सिस आणि त्याच्या खालचा पोर्शन म्हणजे आपल्या फिगर मधला. ओके, दिस इज द फिगर. सो देअर डायमेन्शन आर 50 mm. न्यूट्रल ऍक्सिसच्या खालचं डायमेन्शन आपण काढलेलं आहे, म्हणजेच वाय बार 125 mm इज इक्वल टू YT. ठीक आहे. सो दिस इज द पोर्शन विच वी हॅव कन्सिडर्ड below the neutral axis, and we have to calculate force due to tensile stress. Okay, so we are having the formula. Tensile force is equal to average tensile stress. This is very important. Average tensile stress into area under tensile region. Area under the tensile region, and we know that sigma is equal to P upon A, and if I have to calculate the P is equal to sigma into A. Same I have used here. P means my tensile force, sigma means my average tensile stress, into A means area under the tensile region. But here, which stress I have to consider? Average tensile stress, because this total hatching area, it represents the tensile area. Means whatever the tensile force I am calculating the tensile force at the center of this particular tensile region. I am not calculating the tensile force at this particular neutral axis. I am not calculating the tensile force at the bottom side. I am calculating the tensile force at the center of that particular tensile region. Therefore, I have taken the average tensile stress. म्हणजे average tensile stress काढताना ह्या न्यूट्रल ऍक्सिसला किती स्ट्रेस आहे तो पण घ्यायचा आणि बॉटम साइडला किती स्ट्रेस आहे तो पण घ्यायचा. मग ह्या दोन्हीचा जर ऍव्हरेज केला तर बरोबर ह्या सेंटरला किती टेन्साइल स्ट्रेस येतोय तो आपल्याला मिळतोय. मग सेंटरचा टेन्साइल स्ट्रेस घ्यायचा, हा पूर्ण क्रॉस सेक्शनल एरिया घ्यायचा, मग तुम्हाला काय मिळतोय? टेन्साइल फोर्स मिळतोय. नाउ प्लीज टेल मी, इफ आय हॅव टू कॅल्क्युलेट द ऍव्हरेज टेन्साइल स्ट्रेस, व्हॉट इज द टेन्साइल स्ट्रेस ऍट द न्यूट्रल ऍक्सिस? What is the tensile stress at the neutral axis? म्हणजेच tensile stress म्हणजेच bending stress. What is the bending stress at the neutral axis? What is the bending stress at the neutral axis?
Sigma T.
Bending stress at the neutral axis. जो काय आपला
9.41.
का टॉप पोर्शनला मिळालाय का बॉटम पोर्शनला मिळालाय? आठवतं सिग्मा टी 9.41 हा जो आपण काढलेला आहे तो तुम्हाला न्यूट्रल ऍक्सिसला मिळालाय, टॉप पोर्शनला मिळालाय का बॉटम पोर्शनला मिळालाय?
Bottom.
बॉटम पोर्शन. मग सेंटरला किंवा न्यूट्रल ऍक्सिसला बेंडिंग स्ट्रेस किंवा टेन्साइल स्ट्रेस हा काय असतो? झिरो. मग हा झाला झिरो पहिला. प्लस आपल्याला ऍव्हरेज काढायचा म्हणजे ह्या सेक्शनचा ऍव्हरेज काढायचा, हॅचिंग सेक्शनचा. मग वरचा तर घेतला न्यूट्रल ऍक्सिसचा, खालचा काय घेणार स्ट्रेस? 0 प्लस सिग्मा टी डिवाइड बाय 2 इंटू एरिया अंडर द कर्व. ह्या हॅचिंगचा एरिया काय आहे? 125 into 50. मग हा 0 म्हणजे बेंडिंग स्ट्रेस at neutral axis 0, tensile stress at the bottom side 9.41 divided by 2 into 125 into 50. You will get the tensile force. Tell me the value of the tensile force. 9.41 divided by 2 into area 125 into 50. What is the value of tensile force?
29.40 into 10 raised to 3.
29.40 into 10 raised to 3 Newton. So this represents the value of tensile force which is induced in this particular total region. So I have taken 0 plus sigma t. Please keep in mind here I am calculating the average tensile stress, means I have to consider the tensile stress developed at neutral axis also. Also I have to calculate or I have to consider the tensile stress developed at the bottom side also. मग बॉटमचा घेतला आपण म्हणजे कुठला 9.31. न्यूट्रल ऍक्सिसला किंवा सेंटर पोझिशनला टेन्साइल स्ट्रेस म्हणजे एक प्रकारचा बेंडिंग स्ट्रेस आहे. तर न्यूट्रल ऍक्सिसला टेन्साइल स्ट्रेस किंवा बेंडिंग स्ट्रेस हा काय असतो? 0 असतो. 0 प्लस सिग्मा टी डिवाइडेड बाय 2. वाय डिवाइडेड बाय 2? बिकॉज वी आर टेकिंग द ऍव्हरेज. म्हणजे आलेला टेन्साइल फोर्स हा बरोबर ह्या सेक्शनच्या सेंटर पॉइंटला आला. सो प्लीज टेक इन माइंड whenever we are calculating the tensile force or whenever we are calculating the compressive force, average tensile stress or average compressive stress into area under that particular region. मग तो compressive चा असेल तर area under the compressive region आणि तो tensile चा असेल तर area under the tensile region. Okay, this is about the calculation of the tensile force. Have you understood how the tensile force is calculated by using the tensile stress value? Average काय घेतलाय? तर वरचा पण स्ट्रेस कन्सिडर करायचा आणि खालचा पण स्ट्रेस कन्सिडर करायचा. पण वरचा जर कन्सिडर केला तर सेंटरला बेंडिंग स्ट्रेस हा 0च असतो आणि खालचा 9.41 जो काय आपण काढलेला आहे तो खालचा म्हणजे कुठला आहे? मॅक्सिमम बेंडिंग स्ट्रेस. देअरफॉर 0 प्लस सिग्मा टी डिवाइड बाय 2. Yes, have you understood how to calculate the tensile force?
Yes, sir.
Okay. Okay, now draw the figure. Draw the vertical line first. Sigma t always we have to take on the right side. Therefore, this is the right side. This is the left side. And if I will join this, so sigma t is equal to 9.41 Newton per mm square. And here at the top side, sigma c is equal to 5.64 Newton per mm square. Okay, so this is the stress distribution diagram. Sigma t we have taken at the right side, but तो खालच्या बाजूला असू द्या किंवा वरच्या बाजूला असू द्या. Sigma c also we have taken at the left side. Maybe it is present at the top side or the bottom side. So like that we have to draw the stress distribution diagram. And important thing is that how to calculate the tensile force. While calculating tensile force or compressive force, we have to take average tensile stress or ऍव्हरेज कॉम्प्रेसिव्ह स्ट्रेस. ऍव्हरेज म्हणजे कशामुळे घेतोय तर न्यूट्रल ऍक्सिसचा पण स्ट्रेस आपल्याला कन्सिडर करावा लागतो आणि त्या बीमच्या टॉप पोर्शनचा आणि बॉटम पोर्शनचा पण स्ट्रेस आपल्याला कन्सिडर करावा लागतो. पण इथं आपण टेन्साइल काढताना फक्त न्यूट्रल ऍक्सिसच्या खालचाच पोर्शन कन्सिडर केलाय. पण न्यूट्रल ऍक्सिसचा स्ट्रेस काय असतो? कायम 0 असतो. म्हणजे तो सिग्मा टी असू द्या किंवा सिग्मा सी असू द्या, बेंडिंग स्ट्रेस हा न्यूट्रल ऍक्सिसला 0च असतो. पण खालच्या बॉटम फायबरला किंवा बॉटम साइडला मॅक्सिमम स्ट्रेस हा कुठला आहे? सिग्मा टी. देअरफॉर 0 प्लस सिग्मा टी डिवाइड बाय 2. मग एरिया तर तुम्हाला माहितीच आहे, 125 हा व्हर्टिकल आहे, 50 हॉरिझॉन्टल आहे. I have taken the average multiply by area. I have calculated 29.40. So like that we have to calculate the tensile force. Okay. Yes. Have you understood this particular part, everyone? Anybody is having any problem to understand this particular tensile force calculation?
No, sir.
Yes. What about
No
others?
problem.
Okay. Yes, what about others? Please try to give the replies. Maybe in the chat box. Everyone has understood?
Yes, sir.
Okay. So with this, today we will stop here. We will take only one lecture. Maybe in the next lecture, again, we will take some variety of the problems.